How are we doing, everyone? Come on in. Just having a look. This was just the previous class. Let me get rid of that. Questions while we're waiting for others to come in? Ali's asking if you should be using a calculator for web work, or if everything is meant to be done by hand. Not everything is meant to be done by hand, but you should not be using a calculator either. Because here's the issue with web work. You never know how many decimal places they expect from you. One question, 2 decimal places could be sufficient. The next question, 8 might not be enough. So never round off. Use web work as its own calculator. If the answer is cube root of 2, give web work 2 to the 1/3 as the answer. Don't use a calculator to get cube root of 2 and then plug in the decimal places. It's just going to frustrate you. Do we need to know proofs of limit laws for the midterm and exams? Probably not. Who knows? I mean, look, let me not say anything because we haven't written the exams. And I'm not writing the exams, I'm letting the other instructors write it. Once it has been written, we'll make an announcement. So for now, you should have a look at everything we do in class. You can use a calculator during the midterm. Georgia is asking if we can go over limits by rationalizing. We're going to do some of that today. Michael is asking when questions were simplified to logarithm and he doesn't know how to change the base of log in web work. Well, the answer to that is the same as you change the base on your calculator. The answer is you don't. Calculator only has 2 possible bases, 10 and E, and it's the same for web work. It occurs to me that perhaps we never did mention a change of base theorem. So let me give it to you now. Change of base theorem, which tells you you don't need to be able to change the base on a calculator or anything, because you can always change it using this. The change of base theorem says that if you have log base a of x, you can change it to any other base you want, any base b, using the following formula. So you can change the base from a to any other base b, b being bigger than 0, not equal to 1, using this formula. Isabella is suggesting sometimes web work doesn't work as a calculator. With logs, it only allows integers. No. Web work always works as a calculator. Always. And Dini is asking for an example. An example of what? While you come up with an example of what we're looking for, why don't we go back to what we were doing last? Oh, maybe you want an example of a change of base theorem. Let's do that. Suppose this was the question. Suppose this was the question, log base 2 of 3. There's no way for you to evaluate that directly on a calculator or a computer or I don't know about Wolfram Alpha, but probably not. Well, who knows? I don't want to venture. I haven't tried. But on a calculator, what are you going to do? On a calculator, you've only got two options. Either the logarithm with no base, where it's understood to be base 10. So you can change that to base 10. And according to this is log base 10 of 3 divided by log base 10 of 2. And now you can put that into a calculator and get a numerical answer. Matt is suggesting different calculators may allow you to change the base. Very well, but you don't need it because you have the change of base theorem. And I suspect that that's exactly what they use. Also, if you wanted to, you could have changed that to base e by saying this is log 3 divided by log 2, right? It's a logarithm with base e, and both of these, I'll invite you to get a numerical answer for both and convince yourselves that it's exactly the same thing. There it is. Let's do an example of what we were doing last time. Matthew is page 102, 102. So maybe Matthew and Jordan are having issues with solving something like this. Let's do that first, and then we'll come back to that question. Well, actually, Matthew's asking, do we log both sides? Yes, that's the easy answer. You take the log of both sides. It doesn't matter which log. It can be log base 3, log base 5, log base 10, or ln. Those are 4 obvious choices, but really any base you want is fine. This will allow you to bring the powers down, and then you just solve for x. Because the log of 3 and log of 5 are just going to be real numbers, regardless of what they are. You wouldn't, Michael. You would not solve. You would not. Well, wait. This is. I don't know that this question makes sense for the integer of an inequality. Yeah, I don't know what that question is asking. Because, of course, you know 2 to the x is always bigger than 0. So 2 to the x minus 1 is just going to be 2 to the x, but shifted to the right by 1. So it's always going to be bigger than 0 as well. So it's in fact bigger than 0 for all values of x. Perhaps it was a different question. But let's move on to this. They're asking us to evaluate the limit using those limit laws. We're going to, as a last question here, we're going to justify everything completely. But this is the last time. From now on, we're just going to make use of those limit laws without justification, without resorting to them. Here, the limit of a product is the product of the limits. Right, by property 3. I want to say it's property 3. Not 100% sure that it was, but yeah. And now, these 2 things are just polynomials. So by property 10, we saw that we could just plug in. And this is 2 squared plus 2 times 2 times 2 times 2 cubed minus 5 by property 10. And finally, this is 8. 16 minus 5 is 11. So the answer is 88. All right, let's take a few other examples where we're going to stop. Well, I mean, maybe I'll justify a few things along the way, but I'm going to stop justifying every single step. Maybe not this question, but eventually. Allie's asking, how come we can just plug the value in for this? Well, that's exactly what property 10 says. When you have a polynomial, you can just plug in. and this is a polynomial, and this is a polynomial. So when you have polynomials, you can just plug in, you're good to go. Here, property 4 told us that we can take the limit of the numerator divided by the limit of the denominator. The limit of a quotient is the quotient of the limits, as long as the limit of the denominator is not 0. Now, this is a polynomial, so we can just plug in. And if we plug in, what do we get? We get 9 minus 3. So 9 plus 3 is 12. 12 minus 12 is 0. So now we have an issue, because the denominator is 0. And if we look at the numerator just momentarily, this is 9 plus negative 9. So the numerator is 0 as well. So we have a 0 over 0 here. And this is an interesting case. Let's take a step back and consider this 0 over 0 more closely in the following situation. I said property 10. Suddenly I'm not sure that was actually property 10, but regardless, I mean, it was a property that if you have a polynomial, you can just plug in. I want us to investigate this 0 over 0 business. By considering this simple example. It is property 10, thank you. Consider this example here. When x is 0, this has the form 0 over 0. But of course you understand that any non-zero number divided by itself is just going to be 1. So this function, x over x, is actually equal to 1 as long as x is not 0. And we had this property that the limit of two functions behave the same way if they were equal everywhere except at the actual point. So here we're looking at the behavior of this function as we get closer and closer to 0 without actually reaching it. So this limit will be the same limit as 1, which is 1, right? I mean, if you were to graph this, this looks like the function 1 everywhere except at 0, where it's undefined. So if you're taking values very close to 0, but not equal to 0, which is exactly what we're doing when we're taking a limit, these numbers all get mapped to 1. Its behavior is 1. But now repeat. Suppose this was a 4. If it was 4x over 4, would still have the form 0 over 0. Right? 4x over 4 would still have the form 0 over 0, but when you simplify, you now have a limit of 4. Exactly that. And if it's 14x over 4, it's still of the form 0 over 0. But here, you have a limit of 14. And so on and so on. What's the point here? Knowing a limit has the form 0 over 0 doesn't tell you anything. Anything can happen here. This is known as an indeterminate form. This is known as an indeterminate form, You cannot determine the answer just by knowing it has this form. If you have a limit of 0 over 0, that's where the real work begins. That's where we have to do some work. So let's go back to this question and ask ourselves, what work are we going to do? We understood that it had the form 0 over 0, but these are just polynomials. So you could factor, let's factor these, knowing that -3 is a root. -3 is a 0. So x minus -3, or x plus 3, has to be a factor of both top and bottom. How does this factor? This factors as x plus 3, x minus 4. And then by this theorem that I have alluded to here, by this property of limits, namely that if two functions are equal everywhere except at A, then their limits are the same, right? You can actually cancel this out. We're looking at the behavior as x goes to -3, but never actually reaches it. So you're not canceling a 0 over 0 here, but rather a non-zero number divided by itself. This could be a point of discontinuity. We'd have to see. Have not introduced that term yet. Maybe by the end of today's lecture. Right, but the point is, we're canceling a non-zero number over itself. So something non-zero number over itself is 1. So we're good to go. And now we have something well behaved. Now we have limit of one polynomial divided by another, where the limit of the denominator is not 0. So this is a nice, well-behaved rational function. We can take the limit of the top divided by the limit of the bottom. I'm going to stop doing that from now on because you understood this property to be true, right? This is property 4. And now this is just a polynomial, so I can plug in. And that is just a polynomial, so I can plug in. And we get a limit of 3 over 7. If it was any number over 0, then we could not, if it was a non-zero number over 0, then there would be no hope of cancellation, right? But you know that a non-zero number over 0 in the context of limits is some sort of infinity. So we'd be expecting an answer of infinity, plus or minus, right? Why do we have to go through all the intermediate form if we end up with an answer in the end? I'm just saying that if you have a 0 over 0, anything can happen, right? Some of you may want to cancel the 0 over 0 and say the answer is 1, but you see what happened. In the end, the answer was 3 over 7. I'm just saying that when you have a 0 over 0, there's no cancellation. Anything can happen. And when I say no cancellation, I mean you cannot cancel 0 over 0 here and get an answer. This is an indeterminate form. You cannot determine what the answer is just by knowing it has this form. Work has to be done. Consider this. We again have a quotient, and you know the limit of a quotient is the quotient of the limits as long as the limit of the denominator is not 0. But in this case, easily seeing that the limit of the denominator is 0, what about the numerator? 50 minus 45 is 5, minus 5 is 0. So we again have a 0 over 0. You again have an indeterminate form. What are you going to do? You know what to do. You're going to factor top and bottom. Exactly that. How does the numerator factor? 2x and x. What do we want? Plus 5 minus 1. Sounds about right. 2x squared plus 10x minus 1x. That gives you the plus 9 and minus 5. And then denominator, of course, x minus 5, x plus 5. And once again, so if it's a non-zero number over 0, we can expect infinity, exactly that. Here, these cancel out, right? It's a number over itself. We're looking at the limit as x goes to -5, but it never actually reaches it, right? We're looking at the behavior as you're getting closer and closer to -5. What if we couldn't cancel? Well, that's an excellent question, whose answer we're going to have to postpone for a moment. Right now, we're going to concentrate on cases where you can cancel. So we're left with a 2x minus 1 over an x minus 5. And what do we have? Now the limit of the denominator is non-zero. So you can take the limit of the top, limit of the bottom. These are just polynomials, so you can plug in. And what do we get? Minus 11 over minus 10, or 11 over 10 as suggested by a few people. Questions? How are we doing? Do we have to state that the limit is in indeterminate form? You do not, but I think it's a good idea to do so. How do you get the n numbers? Well, I mean, after canceling this, a limit of a quotient is a quotient of the limits. And these are just polynomials. So you can just plug in. So if you plug in, right, because that's property 10. If you have polynomials, you can just plug in. So property 4 tells you can take the limit of the top, limit of the bottom. And these limits are just limits of polynomials. So property 10 tells you can plug in minus 11 over minus 10, or 11 over 10. And consider this. Again, you've got a limit of a quotient. These are just polynomials, so you know you can plug in if everything works nicely. Numerator, 16 plus 12 is 28. Denominator, 16 minus 4 is 12, minus 12 is 0. You've got a 28 over 0. You know what's going to happen here, right? In the context of limits, you expect some sort of infinity. We have to decide if it's positive infinity or negative infinity. Why don't we take a moment to factor this? This factors as x minus 4, x plus 3. And when x is close to 4, numerator is close to 28. When x is close to 4, this is close to 7. So this is positive, that's positive. The sign is going to depend on this x minus 4. And now you see the issue, I believe. If x is close to 4 but just bigger, this is going to be positive. Whereas if x is close to 4 but just less, then this is going to be negative. So it takes on both values. How are we going to treat that? We're going to consider the limit from the left and the limit from the right, so that there's no ambiguity. For values close to 4, numerator is close to 28. This is close to 7. And for values bigger than 4, a number bigger than 4 minus 4 is positive. So the whole thing, this whole fraction, is positive. But it has the form 28 over 0. So you know it was some sort of infinity. And we have just concluded that it was positive. So positive infinity. You could cancel the x plus 3s, absolutely. But it's not the x plus 3 that's an issue. It would have been an issue if you had taken the limit as x goes to negative 3, and then you could have canceled them nicely and so on. But it's the 4 that's a problem. So you see that the limit as x goes to 4 from the right is positive infinity. Let's repeat with the limit from the left. Now, it's easy to jump the gun and assume you're going to get negative infinity. Don't do it. Don't do it. We don't know. You should not make any assumptions. Don't assume the sign absolutely changes. It may or may not. And somebody is suggesting L'Hopital's rule. We're so far from L'Hopital's rule, it's not even fun. What is happening as x goes to 4 from the left? Well, numerator is still close to 28. This is still close to 7. But here, a number less than 4 minus 4 is going to be negative. So we were expecting some sort of infinity. Positive, positive, negative, the whole thing is negative. And there you go. Negative infinity. So limit from the right is positive infinity. Limit from the left is negative infinity. What can we say about the limit itself? Well, I mean, I have have it here, no reason to rewrite it. So what can we say about this limit? Does not exist. Absolutely. The limit itself does not exist. Vanessa is asking if we had 0 in the numerator, would the answer still have been positive or negative infinity? It depends. It could have been. It might not. There's no way of knowing that, right? If you have 0 over 0, there's no way of knowing what the limit is without doing the work. Well, I mean, I think we discussed the difference between undetermined or does not exist and undefined last time, right? I think we had agreed that for limits, we were going to say does not exist, and for functions, we were going to say is undefined. How would you know the plus and minus infinities with the brackets? I'm not sure what you mean here, but we have negative infinity versus positive infinity. I'm not sure what brackets you're referring to. Let's try another one in the meantime. You're suggesting some sort of interval notation. This is not applicable here. We're not looking for an interval. We're looking for the behavior of this function as x gets closer and closer to 4. So either the function gets closer and closer to one value, in which case the limit exists, or it doesn't, in which case the limit does not exist. And that's what's happening here. Consider this. And if you blindly plug in, right, because it is a limit, if you blindly plug in, what do we get? Minus 2 to the negative 1 plus 2 to the negative 1, which is somehow I feel, yeah, fine. So numerator is 0 and denominator is 0 as 1. So we have an indeterminate form here. You know what to do. Well, I mean, do we know what to do? First of all, you understand certainly that anything can happen. And leaving your answer as this is not acceptable. This is not an answer. This is the form this has. We want to work towards an answer. Let's get rid of these negative exponents here. Let's rewrite these as fractions. Right? When you have a 0 over 0, you understand that that's where the work begins. So we're going to do some work. Let's rewrite this as 1 over minus 2 plus h. This is 1 over 2. The whole thing over h. mean, if you plug in h, I mean, you still get a 0 over 0. We haven't really done anything here. Jordan is suggesting to move these to the bottom. Before we do so, though, I think we need to find a common denominator for the numerator. So let's do that. Common denominator for the numerator is going to be the product what does the numerator become? So this one, I have to multiply by 2 over 2. Right? If I multiply by 2 over 2, I multiply by 1, I'm not changing anything. And this one, I'm going to multiply by minus 2 plus h over itself. I'm multiplying by 1, I'm not changing anything. So the numerator becomes 2 minus 2 plus h. Is everybody comfortable with that? So this is h over 2 times minus 2 plus h, the whole thing over h. Now it was suggested to rewrite this, to bring this down or to bring that up. Let me ask you this, where does the h go? Does the h go in the denominator or does it go in the numerator? You tell me. Where does the h go? There are conflicting answers here. Some people saying numerator, others saying denominator. It's not clear. Let's convince ourselves. A over b divided by c. Let's rewrite this as a over b divided by c. And when you divide by something, it's like multiplying by the reciprocal. So reciprocal of c, 1 over c. And now it's clear. The answer is the denominator. So this becomes h over 2h minus 2 plus h. And now you can cancel the h over h. Right? We're looking for the limit as h goes to 0. We're looking for the behavior of this as h goes to 0. It never actually reaches 0. Right? So again, those of you who may be worried that you're canceling a 0 over 0, you're not. You're canceling a non-zero number divided by itself. It's all good. Nothing to worry about. I mean, this is a mistake that is often made. But now you see how to convince yourself. And next time something like this happens, take a moment, write it down so no mistake is made. What are we left with here? This is limit as h goes to 0 of 1 over 2 minus 2 plus h. And now limit of a quotient is a quotient of limits. Numerator is a constant, denominator is a polynomial. You can just plug in. What do we get? Minus 1/4. Absolutely. So, I mean, I'm seeing some people are taking 133 as well. Let me tell you that 133 is a very demanding course. Well, I mean, 133 for most of you is going to be the hardest course you ever do. So be aware of that. Be aware that it gets much, much, much harder. So you know, I mean, it's a whole new thing for everybody. It's completely different from calculus, but luckily, well, first of all, the material is beautiful. It's beautiful material. And secondly, you're going to want to tackle it as I suggested you tackle this course. Lots and lots and lots of exercises from the book. But, well, I mean, you might find it counterintuitive in the beginning, but you'll see that the more you do, it's a whole new way of thinking. And yeah, so tackle it. Master the material by doing lots and lots and lots of exercise. First of all, I assume that you started out with row reduction of matrices. Let me mention that you have to be an expert in row reduction immediately. So if you're not yet an expert in row reduction, make sure you are by the end of the weekend. And what do I mean by that? When you see a matrix, if I give you a matrix, you have to know how to start immediately without thinking. And then you have to understand what the next steps are going to be, second nature. So if already you're an expert in row reduction, you're on your way. Because the thing you don't want to do is not be able to row reduce, because everything is going to depend on that. So make sure that you know how to row reduce, and make sure you know when to stop. What does it mean for a matrix to be in reduced row echelon form? If you don't know that you have reached the end, that's an issue. So you have to know how to begin, you have to know what to do at every single step, and you have to know when you're done. Row reduction, very simple once you can do it. So anyways, once that's done, then lots and lots and lots of exercises from everything else. And you're going to learn linear algebra the way you learn calculus. I don't know what book you're using, but Nicholson, I feel, is an excellent book. The questions start off easy and they get progressively harder and harder and harder, and it's very well done. Well, speaking of Matrix, yesterday I watched the second Matrix movie, and I watched the first the night before. It was on Showcase. Let's do one more. Nicholson, I think it's spelled differently. Nicholson like this. It's called Linear Algebra with Applications. All right, there it is. Consider this. What does linear mean in the context of linear algebra? And I haven't used that term, but let me use it now to make to relate calculus and linear algebra. The limit is linear. What does that mean? That means that the limit of a sum is the sum of the limits, and the limit of c times a function is c times the limit of the function, right? You know these two properties. These are properties 1 and 2. Together, these are known as the linearity of the limit. And I mean, you know, I said 133 is an amazing course, and the issue is that when you're doing it, you don't always see it. But after you've done it, you realize that a lot of the stuff you do can be rewritten in terms of linear algebra. And that is certainly amazing. What is harder, 133 or 141? I want to say 133 is harder. First of all, there's a tremendous amount of material in 133. And wouldn't you know it, it had already been cut down by a third. There used to be 50% more material in that class. It was a struggle to do all that material. All right, let's stop talking about 133 because not everybody is in 133. I'll be teaching 141 next semester. Well, I mean, it depends. It depends what happens with the borders and yeah, we'll see. But right now I am scheduled for 141. I mean, look, don't let that scare you. There's no reason for you not to get an A in 133. But lots and lots and lots of exercises. So the linear refers to these two properties together. It's called the linearity, the linear property. All right. But you know what to do here. If you blindly plug in, right, you see the denominator goes to 0. Numerator, 16 plus 9 is 25. Square root of 25 is 5. 5 minus 5 is 0. We have a 0 over 0 here. All right. We have a 0 over 0. Well, the linearity, I'm suggesting linearity for limits is property 1 and 2 together. That's all I'm saying. I mean, I had not introduced that term, but it's a term that comes in linear algebra. I mean, it's the first word in linear, and that's what it refers to. All right, there it is, 0 over 0. You see what's going on there? And you you see the issue, right? I mean, there's no factoring here. What are you going to do? It's an indeterminate form. You've got 0 over 0. You need to do something. And Jennifer's suggesting to rationalize. Absolutely. We're going to multiply by 1. When you multiply by 1, you don't change anything. So no harm done. What 1 am I talking about? Something students like to refer to as the conjugate. I'm multiplying by something over itself. So I'm multiplying by 1. I'm not changing anything. And what does that do? Well, observe. What happens to the numerator? This times this. The square roots disappear. This times that. I get a 5 square root. And then this times that, I get a minus 5 square root. And finally, this times that, minus 25. I'll leave the denominator factored. It's probably a good idea that you do the same. Factored is always easier than expanded. So no point in multiplying that out. And you see what happens, right? The 5 square roots just cancel. So multiplying by this conjugate has this exact effect of canceling out the square roots. You're getting rid of the square roots. And you have x squared plus 9. Let me not skip a step. How did we multiply those? It's the usual, right? This times this times that, this times this times that. You're multiplying the FOIL trick, whatever you call it. All right, let's finish that up there. As x goes to negative 4, this is x squared minus 16. And if you want to plug in, you can, for excellent video quality. Questions? We're back. Excellent. So back to this 0 over 0 business. Right? But you know what's happening, right? We're going to factor the numerator. You see how the numerator factors. Factors as x plus 4x minus 4. And you're going to cancel that with the x plus 4 in the denominator. These cancel out. And you're good to go. Jamie is asking why this choice. Was it arbitrary? It was not. You see what's happening, right? By multiplying by the opposite sign, it effectively gets rid of the square root. Your product no longer has any square roots. The square roots have been moved to the bottom. And that's an excellent. That's something very desirable here. And now we're good to go, right? Now we have non-zero limits. Numerator goes to -8. Denominator goes to 10. -8/10 or -4/5. You can multiply by whatever you want, right? As long as you're multiplying by something over itself, it's fine. But I claim this is what you want to multiply by. Anything else will probably not help you. If it was a +5, you would multiply by, well, first of all, if it was a +5, you wouldn't need to multiply by anything because the numerator wouldn't be 0. So you would not have had a 0/0. And that would have been the end of it. If it had been 0/0, then you would have wanted to multiply by this. Chris is asking, since the denominator is not a polynomial, are we still allowed to plug in? Well, this is a polynomial, so you're allowed to plug into that. You have a square root here, and we saw the limit of a power is the power of the limits. And then you saw that the limit of a constant is a constant, and so everything is still fine. The last step, we're just plugging in. Because, we've been using, we had been justifying the steps by saying by property 2, 3, blah, blah, blah. Now we've stopped that because it's too time consuming and you know what those properties refer to. Let's consider another property of limits. Let's consider another property of limits. If you have this inequality, if you have two functions which follow this inequality for all x near a, except possibly at a, then the limits will follow the inequality as well. Wow. I'm jumping the gun here. And limits both exist. Then the limits follow the same inequality. Let me give you a flavor of the proof. What's going on here? Bring the f to the other side. And call this function h. What are we saying? We have this function h, which is positive. So if you looked at the graph, this function would always be bigger than or equal to 0. What can you say about its behavior? Its behavior is, of course, going to be bigger than or equal to 0, right? It cannot suddenly dip down below the x-axis because it was always bigger than 0 to begin with. But this is just the limit of g minus the limit of a of f. So bring this to the other side and you're done. That's the idea. But now this leads to the more important theorem, known as, that did say x near a. This leads us to the more important theorem, known as the squeeze theorem. Suppose you have three functions, f, g, and h, for all x near a, except possibly at a. If the limit as x goes to a of f is L, and the limit as x goes to a of h is L, then the limit of g is also L. I mean, I'm not going to prove it rigorously, but let me give you the idea here. We're saying that this limit is L. So this gets closer and closer to L. So whatever the limit for G is, the limit for G is going to be less than or equal to L, right? That's why the previous claim. And similarly, this also goes to L. So the limit of G is less than or equal to the limit of H. And so you see that this G is squeezed between the two L's. This limit is less than or equal to L, but it's also, it's bigger than or equal to L, but it's also less than or equal to L. So it has to be L. If this converges to L and this converges to L, then this has to converge to L. Let's take an example. It's not 38. Consider this. First, let's ask the question, what is happening? As x goes to 0, what is happening to pi over x? That actually depends on which side you're coming from. Are we going to 0 from the left, or are we going to 0 from the right? If we're going to 0 from the right, from the plus, pi over x is going to, well, it's undefined, but in the context of limits, we're looking at pi over 0, which is some sort of infinity. Exactly. And then the question arises, what is sine of infinity? Right, so if x is going to 0 from the right, this is going to infinity. What is sine of infinity? Well, you know what sine looks like. Sine just keeps on going. And as x gets larger and larger, sine isn't going towards a specific number. So this part doesn't have a limit. But this part, as x goes to 0, this part goes to 0. So this limit looks like 0 times does not exist. Well, maybe you're thinking to yourself, 0 times anything is 0, but you understand the issue. This is actually not the number 0, it's x squared. It behaves like 0 for large values. It's very close to 0, but never actually is 0. But the question is suggesting that the limit still exists. Let's prove it. What do you know about sine? You know that sine is always between -1 and 1. So sine of pi over x will also always be between -1 and 1. Let's multiply this whole inequality by x squared. X squared, which is bigger than or equal to 0. So the inequality is maintained. And we get minus x squared less than or equal to x squared sine pi over x less than or equal to x squared. And now take the limit as x goes to 0 of the right-hand side. What is happening to x squared as x goes to 0? Now there's no ambiguity. Now there's no issue. What is happening to this as x goes to 0? You know what is happening. It's going to 0. It's just a polynomial you can plug in. And when you plug in 0, you get 0. What about the left? What is happening to this as x goes to 0? Again, just a polynomial. You can plug in. So limit of the left is 0, limit of the right is 0. So by the squeeze theorem, the limit of the inside must be 0. How are we doing? Questions? So we've been talking about limits. And what, Ali, was the purpose? The purpose was to figure out what this limit was. And now we have concluded that the limit is 0. So we've been, the final answer is that the limit as x goes to 0 of x squared sine pi over x is 0. Would it be the same if it were to be tan instead? I don't know that you can sandwich tangent between -1 and 1. In fact, we know that you cannot. We've been looking at limits. And you know, I mean, our first definition of limit, right? What is a limit? It's the behavior of this function as x gets closer and closer to 0. How does this function behave? And if you're having difficulties with limits, I mean, it's understandable because we're asking for the behavior. What does this even mean? Behavior sounds more like something you would study in psychology, not mathematics. I'm using the word behavior here. How does this behave? That seems a bit up in the air. We gave a better definition that this function could be made arbitrarily close to 0 by taking x sufficiently close to a. But even that, what does that mean? Sufficiently, arbitrarily, questionable there as well. The issue is that these are not the real definition of a limit. And if you're having issues with what a limit actually is, that might be one of the reasons. So let me give you the real definition of a limit. Definition. We say the limit as x goes to a of f of x is L if epsilon greater than 0 is given. There exists the delta greater than 0 such that if x minus a is less than delta, then f of x minus L is less than epsilon. This is the real definition of a limit. Let's compare that to the arbitrarily close, sufficiently close business. F of x can be made arbitrarily close to L, right? F of x can be made arbitrarily close to L. The difference between F and L is at most epsilon if you take x sufficiently close to A, but not equal to A. There. On a graph, what are we saying? If you take x in here, then the stuff in here is being mapped to stuff in the box right here. Let's take an example. Let's take an example. Let us show, using this epsilon delta definition, that the limit as x goes to 1 of 2x plus 3. Well, first of all, what is that limit? You know what that limit is. There's no ambiguity, right? This limit should be from the work you've been doing. Everyone? Should be 5, thank you. Right, it's just a polynomial, we can plug in, we get 5. Now let's show it using the real definition. What must we show? We must show that for any epsilon greater than 0 given, there exists a delta greater than 0, such that if x minus 1 is less than delta, then f of x, in this case your f of x is 2x plus 3, minus the limit is less than epsilon. What value does epsilon and delta represent? An excellent question. The delta is how close you are to A. So this is A minus delta, A plus delta. By taking values of x, delta close to A, so in here, you guarantee that you map values close to L. It's exactly it. A fancy placeholder, if you will. But geometrically, the delta represents how close you have to be to A in order for your function to be close to 5. How close? Epsilon close. It's the error. So let's start with this. Absolute value of 2x plus 3 minus 5. What is that? That is, of course, 2x minus 2. And now let's factor out a 2 from here. And the absolute value of a product is the product of the absolute values. Absolute value of 2, you know what that is. That's just 2. What do we want to do? We want to make this, which is equal to that, we want to make that less than epsilon. Now, you have no control over epsilon, right? The epsilon greater than 0 is given. You do have control over the delta, though. And this is sometimes referred to as the epsilon delta game. I give you an epsilon, you give me a delta which works. So here you see that if you take delta to be epsilon over 2, right? If x minus 1 in absolute value is less than epsilon over 2, if this is less than epsilon over 2, everything cancels out and you get the required epsilon. Beautiful. So by taking, in this particular example, by taking delta to be epsilon over 2, you have made f of x minus L less than epsilon. Exactly what you wanted to do. How are we doing? Do another example. Why don't we do an example from the book? Well, let's try another example. Where did we get the 2x minus 2? It's from here. F of x minus L. This is your f of x. And that's your L. Exactly that. Consider this. What would you expect the limit to be? You mean this last part? By assumption, x minus 1 was less than delta. So if we make delta epsilon over 7, you're good to go, right? This is just a polynomial. You would be allowed to plug in. 15 minus 1 is 14. 14 over 2 is 7. Let's prove that this limit is 7. What do we have to show? We must show that for epsilon greater than 0 given, there exists the delta greater than 0 such that if x minus a is less than delta, then f of x minus L is less than epsilon. Again, you have no control over epsilon, but you do have total control over delta. All you have to do is show there exists some value of delta, which makes everything work. Try it. See if you can get that value of delta. Let's start with this. 3 over 2x minus 1/2 minus 7. So we start with this. Let's simplify. Maybe a common denominator here. Minus what? 14 minus 15 over 2. You could very well be asked to prove this on a test. Let's factor out a 3 over 2. Leaving us with x minus 5. Is that right? And again, the absolute value of a product is the product of the absolute values. Absolute value of 3 over 2 is 3 over 2. And now you see this x minus 5. This can be made very small. What delta are you going to choose? What delta are you going to choose? Does anybody see it? Anyone? Delta? Which delta? I want to make this whole thing, which is really this, I want to make it less than epsilon. I'm going to choose delta to be. We want to make this less than epsilon. So if you bring this to the other side, you get x minus 5 has to be less than 2/3 epsilon. Right? So if you take delta to be 2/3 epsilon, you're done. If you take delta to be 2/3 epsilon, this is going to be less. 3/2 remains. This is 2/3 epsilon. These cancel out. And you have succeeded in showing that this is less than epsilon. How are we doing? And this limit, where are we getting epsilon? Epsilon is given. We have no control. It's a fixed number. It's a fixed number. And our goal is to make the absolute value of f of x minus L less than epsilon. And it's this epsilon delta definition of a limit that you can use to prove all of the limit properties. Well, of course nobody's getting it, because it's very difficult. And that's why we don't start with this as the definition of a limit. So if you were already struggling with the definition of a limit, I don't know that this is going to help. But that's the real definition. That's the epsilon delta definition of a limit. I'm going to let you have a look at that again. Maybe try a few exercises from the book. We'll pick this up again on Friday. What's the relationship between epsilon and delta? Well, that's exactly the question. Is there a relationship between epsilon and delta? And if so, what is it? That's really the question you have to answer in every single question. Very good. So I'll let you think about this, practice, and we'll do a few more examples on Friday. Thank you all for coming. I'll see you guys then. What page? This is from page 114. You guys have a good one. I'll see you on Friday. I have to go. I'm meeting some people for office hours, so sorry about that. We can answer some questions on Friday.